Okay, guys, so let's remember that the do section has the general specific formulas and then your work and your answer. This is much shorter for confidence intervals than it is for hypothesis tests, so that's nice. So remember, our general formula for confidence intervals is that point estimate plus or minus the margin of error. That doesn't change. No matter what kind of confidence interval we're doing, that is the general formula. So the point estimate is our statistic that we're using. In this case, it's P1 hat minus P2 hat. It makes sense that the difference between the sample proportions would be our point estimate. That's the information we have. And then we're going to add and subtract the margin of error. So I want you to remember way back to when we first started talking about confidence intervals, we said the margin of error is the critical value times the standard error or standard deviation. Okay, so we need to find the critical value, which since we're approximating this with the normal model, that's going to be our Z star value. And again, these are found the exact same way for all confidence intervals using Z star. We use our confidence level to tell us what Z star value to use. A confidence level of 95% or a middle area of 0.95 gives a Z-star value of 1.96. That's the same from previous confidence intervals. And then the standard error, we're thinking that it will be similar to that standard deviation formula that we've been using for hypothesis tests, but now instead of being able to use the true population proportions or even the pooled proportions, we're not assuming that these population proportions are the same. We're not making these assumptions over here that we did for the test. So instead of having to use the pooled proportion, we can just use the regular sample proportions. So we're going to plug in for P1 hat times Q1 hat divided by N1, right? All of the first sample things go together, plus P2 hat times Q2 hat divided by N2. And then we're going to take the square root of all of that. That's our standard error. So again, I want to emphasize that here we are using P1 hat and P2 hat instead of P bar, that pooled proportion for confidence intervals. Okay, that's only true for confidence intervals. For hypothesis tests, we have to use that pooled sample proportion, P bar. Okay, so let's plug in what we have. We know that P1 hat minus P2 hat is 0.15. So we have 0.15 plus or minus. Let's see, P1 hat was 0.55. So Q1 hat would be 1 minus 0.55 or 0.45 divided by N1, which is 200. Plus P2 hat, which is 0.4. So 0.4. Q2 hat would be 1 minus 0.4 or 0.6. And then divided by N2, which is 150. I have to take the square root of all of that. Okay, so I'm going to work that out all in one calculator command. Remember, I'm going to do my lower bound first, so I will subtract first. Okay, so I have 0.15 minus second square root. I'm going to put parentheses around this part here to make sure that those two are separated from each other. Okay, so parentheses 0.55 times 0.45 divided by 200 and my parentheses plus new set of parentheses 0.4 times 0.6 divided by 150 and my parentheses. Okay, and then I hit enter. I get 0.096. Okay, just want to make sure that I typed that all out correctly real quick. I believe I did. Yeah, okay. So I get 0.0967. I'm going to round to 3 decimal places. So 0.097, comma. Let's do plus now. I went up and selected that just a second ago and hit enter, that previous command. So I'm holding down my left arrow key to get all the way to the plus sign. Oh, I know why that's not correct. I'm so sorry, guys. I just made a mistake. I forgot something. Hopefully you were thinking in your head that that does not match the formula above, right? I plugged in this part and I plugged in the standard deviation part, but I forgot the Z star value. Oh my goodness. Okay, so let me scoot this over. 0.15 plus or minus. Now my Z star value for a confidence level of 95%, hopefully you kind of are starting to remember that that's going to be 1.96. But if you don't remember that yet, you can look at your table A2 and come down here to the positive side and see these critical values. So for a confidence level of 0.95, we use 1.96 as our critical value. Sorry about that, guys. Totally messed up my calculations here. It should be 0.15 plus or minus 1.96 times the square root of all of that. Oh gosh, okay, so I've got to type it again. Let me clear this out. It should be 0.15 minus 1.96 times second square root, parentheses, 0.55 times 0.45 divided by 200, and parentheses plus parentheses 0.4 times 0.6 divided by 150, and parentheses. Okay, that looks much better. 0.04, if I round, it'll be 0.046. That matches my answer key over there. Being silly, I made a mistake. Okay, so to get my upper bound, I again go up and select that and scroll all the way over so that I can change that minus sign to a plus sign. And that's my upper bound. So 0.254. All right, 0.254. There we go. That is my confidence interval. Of course, our last step is to interpret that in context. So if you remember, we had that sentence for interpreting confidence intervals. That hasn't changed. It's the same sentence. We are blank % confident that the interval from blank to blank will capture the true parameter in context. So let's put that into context here. We are... our confidence level was 95, so 95% confident that the interval from 0.046 to 0.254. If it makes you feel better, you can convert these to percentages, right? This would be 4.6% to 25.4%. That's fine too. Captures the true, remember our parameter is the true difference in proportions. Instead of writing the females minus males part that I wrote up here, I'm going to go ahead and put what the populations are. So true difference in proportions of females, oh, I should say US. Excuse me, US. Females and males who use Twitter regularly. Okay, that's it. That's our confidence interval. So since we only have just a little bit more to go over, I'm going to go ahead and reference the big ideas that we would fill in on the previous page. So here we go. Learning target number 5 is about constructing confidence intervals. So our new name is a 2-sample Z interval for P1 minus P2. That's for confidence intervals. Again, I'm helping you define the parameter. This part is actually true for hypothesis tests as well. I just didn't want to write it down twice. So P1 minus P2, again, is that true difference in proportions, and you have to put the context. P1 hat minus P2 hat is your statistic, and you also use it as your point estimate. So the specific formula for confidence intervals for a difference in proportions is your statistic, P1 hat minus P2 hat, plus or minus your critical value, don't forget your C star like I did, times your standard error, the square root, and we fill in P1 hat and P2 hat instead of the pooled proportions. Okay, so there also may be some questions about interpreting that interval. So if your interval is a positive number to a positive number, right, and putting plus and plus to indicate positive numbers, that means your first population proportion is greater than your second population proportion. And that was true for us, wasn't it? Yeah, so 0.046 to 0.254, those are both positive numbers. So we're pretty confident that the proportion of US females who use Twitter regularly is greater than the proportion of US males who use Twitter regularly. On the other hand, if they were both negative, I think that would have been the case for our very first example if we'd done a confidence interval. Since they had a negative sample difference, and we had convincing evidence that that Black and Hispanic females were underrepresented, I think we would have had a confidence interval that had a negative number to a negative number. Then the second population proportion is greater. So in that case, the non-STEM students had a higher proportion of Black and Hispanic females. On the other hand, if it is a negative number to a positive number, by the way, it'll never be a positive number to a negative number because we always put our smaller number first. So if it's a negative number to a positive number, then we don't know which is greater. 0 is included, right? If you have a negative number to a positive number, 0 is going to be in there somewhere. And so it's possible there's no difference, but we cannot be sure. Okay, 0 is a possible value, but so are all the other values in that interval. So we actually don't know which population proportion is greater. We just don't have convincing evidence that they're not the same. Okay, that's it for a difference in proportions. Remember, when you're doing your homework, make sure you follow the 4-step process on all 3 of those problems for both the hypothesis test and the confidence intervals, but you don't have to check the conditions twice.